Most data are shown as scattered points on a graph. And while the simplest way to connect them is with straight lines, that doesn't always look very smooth. But what if you did want something smooth? Like a curve with no sharp corners or pointy edges? Well, that's a bit more complicated. You might be thinking of something like Bezier curves, which are pretty standard and are used almost everywhere, such as in animation, CADing, and even in fonts. But I'm talking about something way more niche. Hermite curves are connected splines interpolated between pairs of points. So for a set of 4 points, you would need 3 splines. Let's look at one of these splines individually. Each spline is specified by 4 factors. The first 2 are the points you interpolate between, which we'll call P0 and P1. The other 2 are the slopes of the curve at the endpoints, which we'll call M0 and M1. Since there are 4 parameters, we assume the spline takes the form of a cubic polynomial. You might think that specifying 2 points, each having an x and y coordinate, accounts for 4 parameters on its own, bringing the total up to 6. However, the x coordinates don't need to be treated as free parameters, since you can always apply transformations to shift and scale the cubic so that the correct y values land on the desired x positions. This means a cubic with its 4 coefficients is exactly sufficient, and that there is no need for a higher order term. And here it is. Yeah, quite scary. This form is simplified using the Hermite basis functions, which are these 4 cubics. Let's see how to utilize it for interpolation. Going back to our straight line interpolation, we can figure out the slope at each corner by taking the average of the slope on its left and the slope on its right. For the endpoints, they just retain the slope they had initially. Therefore, this is our slope formula, with the exception of the endpoints. Except, we're going to work with a simpler form of the equation. If you assume x0 and x1 are at 0 and 1 respectively, it boils down to this pleasant equation. But I haven't even shown you the full picture. Take the equation and replace x with t and replace y with coordinates. You have a parametric equation. This is why if you search up Hermite splines, they're usually written with t to signify parametric equations. This equation can now draw smooth curves through sets of points in space. But wait, we need to critique our slope formula. Now that we've replaced y coordinates with points, we need to critique the denominator. The equivalent of the difference in x values on a function is the equivalent of the distance between 2 points on a curve. But we're also going to add in an extra term, 1 minus c. C here represents tension. The curves will end up looking like strings, and increasing C will pull the strings tighter. But enough talking, let's look at one of these curves. In this example, we have 7 points. I'm excluding the segments connecting to the endpoints since the slope formula works differently at those points, but the endpoints still have an impact. Now, look what happens as I make C go from 0 to 1. The splines get pulled tighter and tighter until they end up as straight lines, and it becomes a normal linear interpolation. Anyway, you can achieve some cool shapes. Check this out. If you move the endpoints to the inside, the shape now concaves inward at the opening. You can make stuff like bananas, or even hearts. I've run out of ideas for shapes, but I've attached the Desmos links in the description if you guys want to check it out for yourself. Comment below your graph if you make something cool to boost my analytics. And if you made it this far, thank you. Liking this video would help a lot to push it out to other people, and subscribe if you like this sort of content. Until next time, keep thinking.